Hi, good afternoon. The last thing that we were talking about is elastic potential energy, and here I'm gonna do one of the problems with you. We have a force that is 520 newtons, keeps a certain spring stretched a distance of 0.200 meters. Usually this piece of information is given to you so that you will be able to calculate what is really the K, what is the spring constant, which is, we call it the stiffness of the spring. Now, A, what is the potential energy of the spring when it is stretched 0.2 meters? What is its potential energy when it is compressed 5 centimeters? Okay, always a sketch like this is very helpful. Okay, then the force that is stretching is 520 and it is stretching the spring 0.2 meters. Then K can be calculated as the force divided by X. I did use here the absolute value because I'm interested in magnitudes. 520 divided by 0.2, and that is going to be 2600 newtons per meter. If I want to calculate what is the amount of energy stored, I call this US1. It is 1/2 kx squared, and it's going to be 1/2 2600 newtons per meter times 0.200 meters squared, and that is going to be 52.0 joules. Okay, when we are going to have a compression, like I can use here a negative, but that will not change anything because when you square, the negative is going to be disappearing. Then US2, it is 1/2 kx squared. It is 1/2 2600 newtons per meter times 0.0500 meters squared, and that is going to be 3.25 joules. Now, we sometimes have situations where we're going to have gravitational and elastic potential energy combined, like when you are really, let's say, jumping over a trampoline, or, like there are many situations where we will do that. And I will say, when a situation involves both, then my U total is going to be U gravitational plus U elastic. Okay, we are using in our terms UG and US. Now, the forces can be classified into two major types: conservative and non-conservative forces. The conservative forces, they allow conversions between kinetic and potential energy. I will say few examples are gravity and the spring force. These both are really conservative. Now, the work done between 2 points by any conservative force can be expressed in terms of a potential energy function. It is reversible. It is independent of the path between the 2 points, and it is zero if it is going to be cyclic, or like starting from the same point and ending at the same point. Forces like friction and resistance, they are not conservative. We call them non-conservative forces, or we call them dissipative forces because they dissipate energy. Dissipation means they're going to convert energy into other forms that we cannot reuse again. Now, the work done by a conservative force, such as gravity, doesn't depend on the path. It depends only on the initial and final points. Then the work is the same in all these three paths. Going up this way, going straight, going down is going to be the same. Now here, talking about non-conservative forces, I will say mechanical energy is going to be converted into internal energy for tires, for maybe sometimes it's going to cause temperature to rise, it's going to be maybe sound, light. Non-conservative forces do not store potential energy, but they change the internal energy of the system, which means like I can include them in the conservation of energy, and we can say this is the change in the internal energy of the system, or we can include as the work done by non-conservative. Now, in one dimension, we have a conservative force can be obtained from its potential function, from its potential energy function, using the formula Fx equals minus u over dx. In regions where u changes most rapidly with x, this corresponds to a large force magnitude. And also I will say when Fx is going to be in the positive x direction, u is going to decrease with increasing x. Always the conservative forces act to push the system toward a lower potential energy. Now this is the graph that we can use for elastic potential energy. Remember, we did talk about this before because it is 1/2 kx squared, then it's gonna show like this, and then when we are going to derive it, take the derivative with respect to the x to get the f is going to be a straight line like this. And of course this represents Hooke's law. Also the gravitational potential energy, which is UG equals mgh, can be represented as a straight line like this, and then when I will take the derivative with respect to the y is going to be minus mg, which is a constant, and you know, it is consistent with you know, the rules that we have here. Now whenever we have potential energy in like 3 dimensions, then we can find the components for the force Fx minus the partial derivative of u with respect to x. Fy is going to be negative the partial derivative of u with respect to y, and Fz is going to be negative the partial derivative of u with respect to the z. Now we can actually say that this is the partial derivatives of u. We can have them multiplied by the unit vectors to show the directions. This is the x, this is the y, and this is the z. And then we can maybe write it in a very compact way. That inverted triangle, we call it a gradient. Then F equals negative the gradient of u. Okay, here we have a force that is parallel to the x-axis acting on a particle moving along the x-axis. This force produces potential energy ux given by ux equals alpha x to the 4, where alpha is given as a constant, equals 0.630 joules per meter to the 4. What is the force, magnitude, and direction when the particle is at x equals negative 0.8 meters? First, I need to find the force, and that is by finding what is the derivative of u with respect to the x. I'm gonna put my function here. Alpha is a constant, it's gonna go out of the derivative, and then the derivative, it is 1 over 4x to the cube. Then I can calculate f at x equals negative 0.8 like this, and I will calculate that force to be 1.29, and it is positive, then it's going to be along the positive x-axis. like there is a negative here, and then x cube. When you're gonna multiply negative 0.8 times negative 0.8 times negative 0.8, you're gonna get another negative, and then the overall force is gonna be positive. These are some of the applications. Here we are talking about energy diagrams, and this is a graph showing both the potential energy function and the total mechanical energy. Now this is the potential energy, and this is the total energy E. Now this here, we can say this is UG or U. Okay, now at this point here, from here to here, this is U and the rest is K. Then at any moment, K plus U equals E. At this moment here, or like here, this is K and that piece is U. Then this is really the graph is showing us the limits of the motion, where the points where the U curve intersects with the horizontal line, which is the E, the total mechanical energy. For any graph of potential energy versus x, the corresponding force can be calculated as Fx equals minus du over dx. Whenever the slope of U is 0, the force also is 0, and this is the point of equilibrium, which is here. When U is at the minimum, the force near the minimum draws the object closer to the minimum, so it is a restoring force. This is called the stable equilibrium. Then it's gonna make like the object going back to equilibrium. When U is at the maximum, the force near the maximum draws the object away from the maximum, and this is called unstable equilibrium. I'm gonna do here some problems with you just to show you how we're gonna use the conservation of energy together with the work done by non-conservative. We have 62 kilogram skiers moving at 6.5 meters per second on a frictionless horizontal snow-covered plateau when she encounters a rough patch, and her skis is a rough patch that is 4.2 meters long. The coefficient of kinetic friction between this patch and her skis is 0.3. After crossing the rough patch and returning to friction-free snow, she skis down an ice frictionless hill that is 2.5 meters high. How fast is the skier moving when she gets to the bottom of the hill, and how much internal energy was generated in crossing the rough patch? Now just here I'm drawing kind of a diagram that is gonna show me what is really the problem about. Then like this is the skier. She had an initial velocity, then there is a rough region where she's gonna step on for a while, and then after that she's gonna descend. Now it's very important that we gonna designate here where is the reference for UG equals 0. In all your problems, whenever you're gonna you're gonna solve problems, you should show me where is your G equals 0. I can say here that like this is the most general form of the conservation of energy, EI plus work by non-conservative, which means if I have friction I will include it, equals E final. Now of course in this problem I don't have any springs, then I will try to include the gravitational potential energy together with the kinetic. Then her kinetic is 1/2 mvi squared, and she was at an elevation of 2.5 from my reference. Then she had mgyi as gravitational potential. The work done by friction it is negative mu k mg times d. Remember, mg, it is the normal here. Okay, then and the normal is not always mg. And then this all is gonna equal, when she's gonna come here at the bottom of that cliff or whatever it is, she's gonna have kinetic energy, because at this point here, this is our reference for UG equals 0. I can drop the mass from all, and then my V final can be written as the square root of VI squared plus 2GYI minus 2 mu KGD. I can plug in my numbers, and finally, this is her final velocity, 8.16 meters per second. Now, of course, the internal energy that was, used or like added to the system, it is, the mu k. I don't know why is it looking like S, but of course it's a mu k mg times S, and that is 0.3 times her mass times 9.8 times 0.42, and that is 766 joules. I did not include here the negative because they are asking just about the magnitude, but of course that is work done by friction, and that should be negative. Okay, this is another problem where I have at a construction site a 65 kilogram bucket of concrete, which is this one here, B, hangs from a light but strong cable that passes over a light friction-free pulley. Remember, whenever we are talking about strings here, cables, we are going to ignore their mass. Also, if I have a pulley, I will ignore its friction. I will ignore also its mass. And it is connected to 80 kilogram box on a horizontal roof, like the picture. The cable pulls horizontally on the box, and a 50 kilogram bag of gravel rests on the top of the box. The coefficients of friction between the box and the roof are shown as mu s 0.7 and mu k 0.4. Find the friction force on the bag of gravel and on the box first. Suddenly, a worker picks up the bag of gravel. Use energy conservation to find the speed of the bucket after it has descended 2 meters from rest. Now, I will first calculate Fk. Okay, because I was given both, I want to see which one. Okay, then Fk is mu k mg, which is 0.4, times the total mass, which is the box plus the gravel, is going to be 130 kilograms, times 9.8, and then the force of friction for the kinetic is going to be 510. And for the static, I will say mu s times mg, which is 0.7 times 130 kilogram times 9.8 meters per second square. Okay, and that is 892. Okay, now the force that is going to make that system move or accelerate, okay, is going to be the weight of the concrete, which is 637, based on that mb times g, 65 times 9.8. Okay, now the friction force on the gravel is 0 because there is no horizontal force on it, but on the box we are going to find that the force on the box should be 637. I want you to remember the rule for when I'm gonna have the force applied. If it is less than the maximum force of friction, which is mu s times the normal, then the force of friction equals the applied force. If I will have that object okay, like the applied force is going to be more than the maximum static friction, then I will have that force of kinetic friction. Now, after that gravel is removed, okay, we can say again EI plus work done by non-conservative equals EF. And here I can say MBGH plus MAG, like that mass A was at a uppercase H. And the work done by friction, it is mu K MAG cosine 180, okay, because it's in the opposite direction, times D. And both masses, they're gonna move with the velocity v squared, the final velocity. Then I will say 1/2 MA plus MBV final squared plus MAGH. I can cancel that. Even I can, I can ignore it from the beginning since it's gonna stay the same. Now what I can do is I can rearrange my terms, and then finally I will be able to calculate the final velocity of the mass by rearranging, substituting my numbers, and finally V final is gonna be 2.99 meters per second. Don't forget to take the square root. Another problem here, I have 15 kilogram stone slides down a snow-covered hill, leaving point A at a speed. Then it has an initial speed of 10 meters per second. There is no friction on the hill between the points A and B, but there is friction on the level ground at the bottom of the hill between B and the wall. After entering the rough horizontal region, the stone travels 100 meters and then runs into a very long light spring with force constant 2 Newton per meter. The coefficients of kinetic and static friction between the stone and the horizontal ground are 0.2 and 0.8 respectively. What is the speed of the stone when it reaches point B? And then how far will the stone compress the spring? Will the stone move again after it has been stopped by the spring? Now, step by step, the first one, I want to find what is the speed of the stone when it reaches the point B. This is, again, conservation of energy. I need to set my level at B to be UG equals 0. And then I can say I final KI plus UGI equals K final. I will reach my level of 0 gravitational potential energy. Then I will be able to calculate the final velocity of the object to be 22.2 meters per second. Now, we know that K is 2 Newton per meter for the spring. The distance, it is 100. And then here is a sketch that this stone is coming with the velocity, the V final that we did talk about, and then is gonna encounter that area, rough area, and then finally is gonna stop. I will say EI plus work by non-conservative equals E final. I have 1/2 mv final squared, and it will lose this amount of energy, and that equals 1/2 kx squared. I can rearrange the terms, and finally I will have an equation that is a quadratic equation, because it's going to be in the form of x squared plus 29.4x minus 756, and then I have, this is the solution, 16.47. This is one solution. The other one is negative 45. then I will say, if I will consider this number here, it should be like 16.5. Okay, then F elastic, I need to calculate that, is going to be 32.8 Newton. And if I will calculate what is the maximum force of static friction, is going to be 118 Newton. Then it is more than the spring force, then it's going to stay at rest. It will not go again in the opposite direction. Okay, this is including the whole chapter of 7. Thank you very much and have a great night.